Yeah. Oh, I love those.
It's gonna be a good one.
Quantum tunneling.
It's not.
And I have to
S'mores.
specify
S'mores.
for them
S'mores.
who doesn't know.
Whoa!
That's what I hope to get out.
You're impressed.
So transistors are basically they're small switches, and they have two modes basically. One's off and one's on. 1 and 0. And they're often found in computers.
Is one off or one on?
One can be on.
Kevin is off, so don't worry about that.
It's okay, I'm on.
Is it vice versa?
Okay, just go.
Okay.
Just ignore the man in the chair back there.
Basically, they're programmable switches that can help us do things like display an image on a screen, that kind of thing. And billions of them are used just to run basic computers now because there's a lot of processes that have to be done. The depletion layer, if you look at the first diagram, it's the P-type base. It's just it's the base. It separates the collector and the emitter. And this basically allows for the switch to be controlled because we put a voltage through the base that allows it to pass electrons through the collector to the emitter. And the base acts as an insulator, but it's doped with silicon, and I'll get more into that later. Tunneling is basically, since we have extra electrons in the collector and the emitter that want to get to each other, but the base prevents that. And basically, without the base preventing it, if the base is too small, then quantum physics kind of messes with us. And quantum tunneling is basically when the electrons move when we don't want them to, and then we lose control of the switch because they're just moving. Moore's law is a very important part of this because it states that around every 18 months, the calculations that can be done by the average computer will double. Which is why, if you look at a computer from 20 years ago, no one's going to buy that versus a computer from 5 years ago. It's because the calculations that have been done have improved so significantly. And in order for them to improve, they need to get smaller. And when they get smaller, we can fit more onto an integrated circuit. You can do more processes, and that's why a lot of computers always have quad core and 1.6 gigahertz. That's how many billion commands they can do in a second. And how many cores they have is basically they can do this many calculations times 4 times a billion. Sine waves are something I'll get into in the when I'm drawing it, because it gets a lot more complicated. But it basically can be represented as an electron. Don't worry about the GIF for now. Look at this diagram. This diagram basically is 2 electrons, 2 barriers, and their probability. Now, an electron, if represented as a sine wave, which it is usually in physics or quantum physics, because it can be mathematically calculated, but represented as a sine wave, we can see the highest probability of it being there at that point in the universe. Right here would be a high probability of it being there. But right around here, it's not as high, but it's still probable to be there. Since electrons are moving at almost the speed of light, it's really quite impossible to pinpoint the exact location. So we represent it as a possibility, which we do a lot in math. Now, quantum tunneling is what you see all across the screen except for the words. The barrier right here, if we look here, so the probability is high because the electron still has enough momentum and energy to just be in that vacuum or air. It doesn't really matter. But when it hits this barrier, it's going to lose its, let's go to this one. It's going to lose its probability, only its probability. If we look over here, when it hits the barrier, we can see that a majority of the electron bounces back, but there's still a small probability of it being on the other side. This would be the narrow barrier one, the one with the shorter one, or the narrower one, yeah. So it's not represented here, but in the GIF it is, where we see a little bit of probability still on the other side, but we also have majority bouncing back. So it's not 100% definite if it's bouncing back or going through. So it all depends on both the size of the barrier, the amount of momentum and energy of the electron. And again, this is all probability, so nothing's absolutely definite ever, really. Yeah, I forgot I did a transition. I was scared it didn't work. Transistors break. When I previously mentioned transistors, And we saw that diagram, like, there's so many. There we go. That one. How there's that P-type base in the middle that prevents the electrons from the collector and the emitter from passing through and breaking the switch. Okay, transitions. Now, the controlled flow of electrons is what we have as a regular transistor, one you can hold in your hand. But when we get down to like the really, really, really microscopic level, when we have to use like electron microscopes just to look at a little switch, it gets to the point. It gets to the point where we can lose the flow of electrons through quantum tunneling. Quantum tunneling usually takes place when the barrier is between 1 to 7 nanometers. Under 1 nanometer, it's not even a barrier anymore. It's just a bunch of electrons. Because to give you a reference point, an atom of silicon is about 0.3. So under 1, it's really easy for it to just the electron to just pass by. But past 7 is usually your safe point. 1 to 7 nanometers is your freaking out zone. I think that's it. Nope, it's not.
Yeah.
So, transistor was first invented in around the 1945 kind of time. So it's been around for quite some time, and we've made some huge innovations to it and some advancements from when it was a vacuum tube to now you literally can't even see it. There's billions in my computer right now doing all sorts of things. And so, like, we can't really upgrade it any more than we have just by doing it the old method by making it smaller, because quantum tunneling is becoming an issue. And with the newest Intel Core, I don't know if you guys have heard, but the Intel Core i9 is actually so highly priced because it keeps breaking.
Really?
Yeah, it keeps breaking because the transistors are so small and they haven't fixed this problem that quantum tunneling is creating a loss of electrons. Therefore, they're breaking, and we don't have the control over the switches. So, really, you're just buying a degrading i7. How can we prevent quantum tunneling? Well, like I said, quantum tunneling happens between a space of 1 to 7 nanometers, really small. So in order to do that, we need some like evolutionary material. And like I mentioned previously, Moore's law is that basically states that every 18 months the transistors will, calculations done by computers will double. But in order to do this, really, if we want to keep our computers as small as they are, like a phone, we're going to have to shrink them even further. And that's it for that. But it's not over.
Nice wallpaper.
Oh wait, hold on. I wonder if I can do this back.
Oh my god, with the cracking of the knuckles. Does that say Mermanite?
Oh yeah, Mervin Ian. Okay, so if we wanna, let's get that picture of transistors back in your mind. I wonder how fast this is gonna go. Oh, relatively fast. Okay. So we have a collector, we have an emitter, and then we have the base connecting them.
Cool.
So, boop, boop, C, G,
Bada bing, bada
B.
boom.
So, the base is what connects the collector and the emitter, making this whole thing work, really. Now, if we look at a larger version, where I can actually do things, and I know I need this one,
Oh my god.
if we have it like this, there, if we have it like this, kind of like a flag, we can have, for the collector and the emitter, they're both doped with a certain thing. And I know it just became legal pretty recently, but that's not what I'm talking about. Ha! See?
Wow.
What I am talking about, though, is it's doped is basically when you force elements to bond with each other. So
Same
the
thing.
transistor is primarily made up of silicon, which is Si, and that has 4 valence electrons, which basically means it has 4 in its outer shell, which is a bunch of chemistry that I don't like to do, so I tone it down to 4. So right now silicon, if it bonds with itself, you can just have it like 1, it's got 4 of these bad boys, and it's just going to connect with 4, and then they're going to connect with 4, and it's just going to create a whole tetrahedron, and it's not going to help us, because what we need is electrons to flow from here and go to here. And without like a hole or something to move it between, we don't have that. And since silicon forms a perfect tetrahedron, there's no hole. It's just solid structure. So what we have in the collector and the emitter is we have silicon bonded with phosphorus. Phosphorus has 5 valence electrons. And since we bond the 5 with 4, we get 1 extra just kind of floating around. That gives us our extra, so 1 minus, because chemistry is stupid. So it's minus when it's really 1 plus. So we have 1 extra electron in both of them, which allow for the switch. But in order to prevent them from moving between each other, we need a proper base. And if we just have silicon, it's going to perform its tetrahedron, not move any electrons. If we bond it with something that has less than 4 electrons, say boron, which has 3, we then have a hole, so 1 plus, because again, chemistry is stupid. And so we have 1 less electron in the middle, but considering the fact that silicon is a metalloid, and we have and primarily the base is all of it's made out of silicon, we see that it's a metalloid, and so it can either be an insulator or a conductor, and we do that by giving it a little base to this thing, or we give it a base voltage to that, and it connects the two and allows for the switch to be a switch. So it's going to get a lot more complicated really fast. So hang on to your seats. So something we can use, well, basically since we have the extra ones here, and they want to meet each other, the base prevents that, on the ones that you can just hold. But if we have it down at like the quantum level, or the I forget what it's called, the quantum realm, which is that Ant-Man term that's been used a bunch, it's basically like 100 nanometers in scale. So if you look at like a map, and it's like 1 centimeter equals like 100 meters, that kind of thing, that's a scale. If we look at a picture of the quantum realm, it could say like 1 centimeter equals like 1 nanometer, that kind of thing. So the quantum realm is just a very, very, very small space, which is where we primarily work with quantum physics. Now, when the base in the middle, this thing, when that gets too small, the electrons flow freely because of quantum tunneling. There's no literal base to prevent them from crossing through. And a good way to detect this, or to even see electrons moving, is using a device called an STM, or a scanning tunneling microscope. And I'm not going to write all that down. I'm just going to write STM because I don't have the time or patience to write with my pen and my phone. So an STM, which is what I'm going to refer to as a lot, is basically, it's a scanning tunneling microscope. So it scans for tunneling on microscopic scales, right? It makes sense. So since we're using quantum physics in this whole thing, and it's becoming a problem, it just makes sense for something that would detect this kind of problem. And the way for it to actually... Let me just draw it out really quick. So I'm going to draw a basic diagram. In my actual presentation, I had like little handouts, and they had all the diagrams on it, but I got to draw everything. Anyway, so this is... Okay, calm down.
Read your audience, Ian. Read your audience.
And I thought I was the miniature one in here.
It was Ethan started it.
Alright, so that... Okay, guys.
This is physics, okay?
That's it.
People's minds are wandering. Just keep going.
Ay, ay, ay.
Okay, so we have the tip of the STM, and then we have the sample below us. So what we want to do is we want to conduct electricity through the tip and the sample, and this basically gives us sort of a circuit. And if you've ever used magnets, and you put them close to each other, they're going to start pulling before they're even connected. Same kind of thing happens here, is we have a circuit without any physical connection. And this happens because this distance, I'll highlight it, that distance right there is between 0.3 and 0.5 nanometers. So about...
That looks so wrong.
So about the size of a silicon atom, or greater. It's very, very, very small.
Very.
And basically, what we are detecting here is if we draw a little. Liv, if you'd like to take this presentation away, I'll give you the pen. Anyway, so if we have our graph right here, which is going to load in just a second, we have two kind of variables, and detected from. Let me just move over here so I can point to it. Detected from here is the intensity. And for the STM to work, it needs to be at that small space because it basically produces a level of quantum tunneling in which allows us to collect data and detect where these electrons are. These are basically atoms. So let's say we put a voltage into the tip of like 2 volts. This is like the standard kind of base voltage for an STM, but like I said, in order for it to work, we need to put voltages into both of them, and they need to be the same, or else the circuit's not going to work. So we have our 2 voltages, and since it's at a certain distance, we have our data, which is going to load. Yeah. So let's say this is just an average line, but for the 2 volts, let's pin it at around that. So this is the intensity of our 2 volts, and this is the intensity. So it's like 80% quantum tunneling because we have such a high voltage on it. The way this kind of factors in with that is if we apply the same kind of circumstances or scenario of a transistor, we can get a much more accurate and a much more usable source of data. Let me kind of explain what I mean. Now the base voltage of a transistor is around 0.7 volts. So it's still relatively a large amount of volts for such a very small thing. So of course there's going to be a lot of quantum tunneling happening because like just approximately this is how much of an intense quantum tunnel there is for just 2 volts. But since we've changed our voltage to match that of a transistor, we're going to have our voltage, and I'll put it in another color, right around like here, just eyeballing it. And if we go back to our transistor, this is basically the intensity of the quantum tunneling of a basic transistor. So now that we know that, we know how probable, because we're using math, how probable of a quantum tunneling there could be in a transistor. And obviously, the i9s are still available because, or the like Intel Core i9s, because they're breaking, because the transistors are too small. The reason they're still available is because they do still work.
Dead battery.
Yeah, I just fell asleep. There we go. The reason the quantum tunneling happens in the STM happens mainly when there's a voltage applied to both sides. Much like the transistor, when the voltage is applied in the middle and connects both sides, it allows for that quantum tunneling because there's a voltage being passed through and there's a movement of electrons. The reason it happens at the STM, same thing. There's a voltage applied to both sides and it allows for that kind of movement. Now, a way to kind of prevent quantum tunneling is using a different element to supplement the very small base, because the smaller the transistor gets, the smaller of a barrier you're going to have, and the less the higher probability that it's going to just pass right through. A good element that we can use is aluminum, and since that has only 3 valence electrons, much like boron, it still leaves that hole in the middle, but since it's also bonded with silicon, it's still a metalloid. Aluminum does conduct electricity very well, so we need to be wary of how much we're using, and since its valence is only 3, we can use the same amount as we do in boron, so we still get that kind of hole that we get the boron. So electrons can still move through easily. And a very important part about this is that, I don't know if you've ever heated up a Coke can, it should expand quite a bit. So if we have, let's have a new transistor, kind of like this. But we have this and this. This is our phosphorus. Silicon, same for this one, but it's backwards because my brain doesn't move that fast. And then instead of this whole depletion layer, which is the middle, wait, where is it?
That's probably the script.
It's just loading in. Anyway, so here and here we have our regular depletion layer, which is silicon and boron. But right in the middle, we have our silicon and aluminum. By the way, this is what I want to fix this. This is my solution. Basically, it's the aluminum in the middle is going to, once it's obviously supplied that voltage of 0.7, which I said is relatively a lot for such a small switch. Once that voltage is applied, I don't know if you've ever just used your laptop or your phone for like hours and hours on end. It starts to heat up quite a lot.
Yeah.
And the reason like almost any computer you can get has a good quality fan is because without a fan, there's a good chance that your CPU is going to burn out in under a minute. And that fan just kind of keeps it cool because you have so much electricity being used at once by like these billions of transistors that it ultimately is going to create so much heat that it's just going to destroy your entire computer. The fan obviously keeps it cool. And once you've used your computer, let's say like I'm using my computer right now and I've used it for the past like 12 minutes. So it should be at a good like 35 to 45 degrees Celsius. And obviously, like if I touch my computer, I'm not gonna burn my hand. Stop turning off. I'm not gonna burn my hand, obviously. So really, what that temperature is referring to is the actual CPU, which you can't physically touch because it's protected by a fan, which obviously helps the other hardware in it that doesn't burn. And the reason that 35 to 45 is such a great number is because that's going to heat the aluminum up to a certain point where it's going to expand, but not too far. And the fan, hopefully, should keep it at that kind of range so that the aluminum will expand, therefore leaving quantum tunneling a little farther, giving it a lower probability of happening. And with the aluminum expanded, less electrons are going to have the possibility of moving through, and we're still going to keep that controlled amount of controlled flow of electrons, while also keeping our transistor in its way. Once let's say I turn my computer off, the aluminum is going to go back to its normal state and no longer expand, and then the transistor will be the same size as it once was. And since we have, let's go back up to here. Since we have, like, you're using your computer more and you have a lot of voltage going at the same time, it's going to heat up even more and expand more. So if you are to use your computer for like 5 hours straight doing like intense like gaming or something, you're using a lot of transistors and power, it's going to heat up so that quantum tunneling is like the lowest possibility of existing. But again, like we're using complete probability, so there's no absolute ruling it out of the picture. Because again, if we want to get that nice, very, very, very small transistor, we can't get that without it having. We can't get that without having at least something there. So we need something there to block the electrons, and with the new one, with it expanding, it allows for the transistor to be small. But it allows it to expand if we need it. And, yeah.
Yay!
All my college.
There you go.
Right? He's good at explaining it.
Yay! Everybody say hi.
What are the risks
so
of
happy.
it expanding? Like, how much would it expand?